Right, good morning. Just a very quick video from me, probably the first of a series designed just to help you guys learn a little bit at home and just to give you a little bit of sort of tutoring in terms of the stuff which we're covering and the exercise which you need to be doing. First things first then, obviously lots of you were in last week, so you've probably already heard this, so you don't need to watch it. But specifically for those people who weren't here, I'm just going to talk for about 5 minutes on chapter 1 from book 2, the statistics chapter. And it's sort of all about regression, correlation and hypothesis testing. Some of which we've seen before. We saw correlation in chapter 4, I think, year 1. And the idea in that chapter certainly was the idea of linear correlation between bivariate data. And we looked at the line of best fit, or the regression line as we tend to call it when we're getting a bit more grown up, having a general equation of y equals a plus bx, aka y equals mx plus c, but a plus bx for regression. Now, the idea sort of underpinning the start of this second chapter on regression is the idea that unfortunately not all bivariate data is linear in its nature, and therefore we need to be able to model such data potentially using other sorts of mechanisms. I'm just going to quickly flip this round so you can have a little look at some of the stuff which I've written down. And the idea is certainly that if we just consider the diagram on the left, clearly that data there is linear in its nature, and so a regression line will be adequate. On the right-hand diagram, however, if you consider data looking a bit like that, the line of best fit, the regression line, doesn't look so clever, and clearly, therefore, an exponential model would be much more sort of suitable to modelling said data. Now, our regression line is a good way of starting off, and we want to keep it like the understanding which we already have. And so we're going to use two models to basically transform our exponential data into linear data. Y equals ax to the n and y equals kb to dx are sort of two models you might already recognise, hopefully, just general formats. But if we sort of, using logarithms, take sort of codes of various data, we can transform those into the models on the right. And what's going to happen there, just flipping you background, is that we're now going to have linear data again. Okay, so that's going to be really, really helpful for the first exercise. The idea there is that we're transforming our exponential data or non-linear data into linear data, or into at least a linear picture using logarithms. And so that's the idea underpinning 1.1 exercise 1a. Now, moving forward, the chapter sort of then looks at a numerical value for correlation, and in the new A level, we don't look at Spearman's rank, we look at something called the product moment correlation coefficient, PMCC for short, and we use the letter R to refer to the PMCC for a sample, which generally is what we're sort of looking for. Now, you are familiar, presumably, with words such as strong positive, strong negative, weak negative, just no correlation, i.e. describing correlation with words. What we're looking here is to add a number to sort of said understanding. And the PMCC ranges from -1, which is perfect negative correlation, to +1, which is perfect positive correlation. Obviously, 0 is no correlation whatsoever. Just sort of considering some sort of words to attach to that. Generally, if we've got sort of 0.7 or -0.7 to 1 or to -1 respectively, we consider that a very strong correlation. Okay, so that would be strong correlation of some description. Now, in terms of sort of working out your PMCC, I just wanted to sort of show you how to do that on the calculator, which I know you all have, so do bear with me. I know this is a little bit of a bodge. And I do want to sort of just underpin, again, the thing I was just saying about the first bit of this chapter. So hopefully this will help you sort of in your understanding of that. So bear with me 1 second. So I've loaded up some data on the calculator. We're going to use statistics 2 as our sort of menu option. And currently I've just loaded in a series of data into our calculator, into the first two lists. Now, to work out the PMCC on our calculator, what we're going to do is we're going to press calc and we're going to press regression. We want regression in terms of x, so we're going to use x, and our general model as described in chapter 4 from year 1 is a plus bx. Now, the data there currently is just in terms of t and e. It hasn't been coded, it's in its simple format, and so we're looking for r as described, and we get a value of r there of -0.7677. Now, that is decent correlation, but I just want to sort of show you what I meant when I said we can code our data. Now, this data we can actually code using the model E equals AT to the B. And so to do that, we're going to take logs of both sides. So just bear with me 1 second. I'm just coding the data, and you can use your calculator to do this. Hopefully won't make any mistakes. And if we're going to code both variables in this instance, hopefully what we're going to see is actually that using coding and considering an exponential model, we can actually get much better understanding of the relationship between these two sets of data. So, almost done. Okay, if we press a plus b to dx now, we now get a correlation coefficient PMCC value of minus 0.999. Okay, so just using that coding element, we can immediately get a better understanding and a better description that actually a linear model isn't the best model to describe the relationship between that data, and actually would be better considering that using an exponential model. Okay, so that's the first two sections of this book, this idea of coding data, and then secondly, the actual value of correlation, which we can put on different variables. And it finishes this chapter with a section on hypothesis testing. Now, we've seen hypothesis testing before in relation to the binomial distribution, and a lot of that is still consistent. For example, we still have a null and alternative hypothesis, H0 and H1. We are still interested in this idea of sort of, a test value, which we're going to actually look at, and possibly this idea of a critical value or critical regions, which we can maybe pick up from some tables. So just having a very quick look at that, the first and most important thing to consider is that, as I said earlier, we use the letter R to denote PMCC values for a sample. Now, actually, our hypotheses in this instance are actually in terms of rho, which looks a little bit like the letter P. Now, rho represents the PMCC, the correlation for the whole population, okay? So you can sort of just see the subtle difference between R and rho. Our status quo, our null hypothesis, is always to assume that there is no correlation between two variables which we are looking at. So our status quo is always going to be, for these hypothesis tests on correlation, rho is 0. Now, you're already familiar with the idea of one-tailed or two-tailed test, and so our alternative hypothesis can be greater than 0, less than 0, or indeed not equal to 0. Okay, and obviously if we have a not equal to 0, we're considering a two-tailed test, and we're going to have to split our significance level at either end of our distribution. Significance level is still pertinent, so for example 10%, 5%, etc. We're going to still look to use that. Now, key thing which is new slightly here, obviously in the binomial, our distribution is x distributed binomially n comma p, so we get kind of the number of trials there. That's not given in the distribution format here. We're told the number of items in our sample over. So we're going to get a sample number, and that's really, really important as well, because it's going to give us sort of the values which we're going to need to consult in our table to pick out the critical region. So if we just have a very, very quick look, I'm just going to show you the tables in the back of your book, which you're going to use for this. We're looking for the table which sort of says product moment correlation coefficient critical values. Now, for example, if we consider a sample level of 20, okay, so we've got 20 data points in our sample. What we're looking at here is all of the different significance levels. So, for example, a 5% significance level in the 20 sample, we would be looking at a critical value of 0.3783. What that infers is that, as we said, we're assuming that there is no correlation between our two variables, as our status quo, rho equals 0. But if we get a value, depending on which end we're at, that's modulus value, by the way, 0.30783. If we get a value, our test value of R in our sample, which is greater than 0.3783 or potentially less than minus 0.3783, we're going to change our mind, we're going to reject H0 and we're going to accept H1. Okay, so the mechanisms of the hypothesis test work exactly the same way, but we're going to use the table in this instance to work out what our critical value and therefore what a critical region is for hypothesis testing and correlation. Right, gents, do let me know if you've got any queries. I hope that was helpful. We'll sort of consider doing one for chapter 2 on probability very shortly as well. Right, stay safe and enjoy. Thanks.